Okay, so today Ning and I will present a theorem, a fundamental result in topology, which is called the Theorem of Classification of Surfaces. So I will shortly present the subject. So we define a kind of topological space, which are polygonal regions whose sides have been pasted. The goal of our theorem is to classify those constructed space. This means that we list all the spaces that are homomorphic with our polygonal regions whose sides have been pasted. So I specify that we will not prove the theorem.
Maybe one question. So if we don't understand some of the words, like whatever, homeomorphic, right? At what point we should get worried? I guess at the moment we shouldn't be worried, but maybe you tell us that some words are really essential for us to understand. Then we ask questions. Because already
Okay.
now,
Yeah,
right? We can start asking many questions. What does it mean homeomorphic? I forgot the edges were pasted, like kind of.
we'll define this. We'll define this.
Okay.
But we suppose that you know what homomorphic means, and if you need to know the definition, I can tell you.
I mean, you can choose. You can either give us a definition, or you can maybe approximately explain to us for you to choose.
Okay. I will define what polygonal regions are. Ning will speak about labeling of a polygonal region. I will discuss about a difficult concept, which is the quotient space. She will underline the importance of the proper labeling scheme. I will define elementary operation. Then she will do the labeling of the sphere, the n-fold torus, and the m-fold projective plane. And finally, I will present the classification theorem. So a polygonal region is a polygon in the plane with its interior. So we take the interior of the polygon, and all the vertices must lie on the same circle of radius r bigger than 0. So in particular, P is convex.
Okay, so let P be a polygonal region that we have just defined with successive vertices that we name in the trigonometric direction with the names P0 to Pn. At the end, give Pn and P0 the name Pn with n being the last number of the series. We need to give it this name in order to name the edge Pn-1 Pn. And we give a label to each edge that we name by the two vertices defining it, for example, P0, P1. And we always name by PK, PK plus 1. Every edge is given a label of the form AK with K a natural number. The labels are usually letters. And note that a label can appear many times, and that we will use this property to do some operations later.
Sorry, I have a very silly question. Which direction is trigonometric? Clockwise or counterclockwise? Just for me to know. Sorry?
Counterclockwise.
Counterclockwise. Okay.
So in particular, the vertices, so the point P0 will be defined with the center of the circle, and we give arbitrary angles.
Okay, thank you.
Okay, so each label has an orientation. For example, the edge named P0, P1 can take the normal direction. That means the direction of the trigonometric direction of naming the vertices. So from P0 to P1 in this case, but it can also take the inverse orientation. And so in the Antoine. Yes. So in this figure, this triangle with given labels, and we observe that a direction is given for each label. In the next figure, this is a unit square with given labels. And we observe, as for the triangle, that a direction is given for each edge. And that is why we introduce the notion of exponents. Two possible directions are given, 1 and -1. 1 is for the normal direction and -1 is for the inverse direction. For example, the label given to P0, P1 will be 1 if the direction is from P0 to P1, and it would be -1 if it's from P1 to P0.
Sorry, default direction is this famous trigonometric direction or not?
Yes, the default direction is
Okay.
trigonometrical.
Okay. So you see, I'm asking a question because it looks like it has many names.
Yes,
so
yes.
That's why.
Yes, just the default is the trigonometrical direction, so the counterclockwise direction. Okay.
So a quotient space is a set with a topology on it, which is relative to a quotient map. So we will pass through the details to go on our specific quotient space. So in our case, the quotient space will be obtained by passing the edges together of a given polygonal region. So what do we mean by passing edges together? This is just defined by an equivalence relation. So this equivalence relation identifies by pair elements of the sides that we want to paste.
Maybe, again, a stupid question. Of course, English is not a mother tongue for all of us, but how is it paste? Does it mean glue? I mean,
Sort of.
Yeah, that's what I would imagine.
Yeah, yeah.
So by pasting, you mean that you take those two edges
we take those two edges and glue it, yeah,
and identify them.
And and this identification is been doing by an equivalence relation.
Okay.
So before we start to detail the equivalence relation, it can be shown in the plane that two line segments are homeomorphic. So say the homomorphism is H, and an important fact is that H can be chosen to preserve the orientation. That's very important. So the equivalence relation is defined as follows. So firstly, we decide that each point lying in the interior of P is only equivalent to itself. So that doesn't change for the point in the interior. And secondly, if we let Q to be a point on an edge of P, Q will be equivalent to its image to the homomorphism H that link the edges that we want to paste. So if we have two edges labeled A, we can paste it by, we can do an equivalence relation and the homomorphism that link those two edges will be the function H here that will be equivalent. Yeah, I don't know if I'm clear enough, but yeah. So the resulting set, which elements are equivalence classes, will be our quotient space, or more meaningful, our identification space. So P quotient will be equal to the union of all the points lying in the interior of P, and union all the pair composed of each points on the boundary and its equivalent one through the homomorphism H.
Maybe again, just for this second term. So when you say a pair, so now this pair is just one point in the quotient, right?
Yeah. So in the quotient space, it will be one point.
Mm-hmm. Maybe I don't know whether I'm allowed to ask nasty questions, but how is it? There are also those corners, right? You're right.
Yeah, those corners. Yeah, those intersections.
Let me just ask the question, because okay, maybe you already understood what I want to say. You know, when you glue or whatever, paste or whatever, identify the two edges, then of course there is a point in the middle of one edge and its sister point on the other edge, and you identify them. But the endpoints on the intervals, right? Maybe they are identified many more times.
The boundary, in fact, so each homomorphism, so each homomorphisms that link two edges can be defined to not those points on the corner won't be equivalent to two elements. It just will be equivalent to one element. And the intersection of the edges and the union of all homomorphism that won't destroy that.
Okay. Forget my question.
Okay.
I have a question. Can you take a sheet of paper and just illustrate what happens if I take one square, let's say, and you identify the top, and then you identify top with bottom and the two sides, just so that we can visually see this.
We will see that furthermore in the slides.
Okay.
Just about your question before, there is a lemma that we can use in order to resolve this problem of multiple points. So we can use the pasting lemma.
Yeah,
I know you know that, Antoine, to have a big homomorphism between the boundaries.
So here are two examples. We can take a triangle region and paste the edges labeled A to see that it is homomorphic to the unit disk in the plane. And one can take the square region and paste it along the edges labeled A and B to finally see that the resulting space is homomorphic to the sphere.
Okay, so when a label appears exactly twice in a labeling scheme, this scheme is called a proper labeling scheme, and that is its definition. If the labeling of a polygonal region is proper, then the quotient space is locally homomorphic to R2. And should I define what does locally homomorphic to R2 mean or not?
Well, I don't know. How is it? Maybe that's for other participants to judge. I mean, right? Informally, it looks like a piece of R2, but I mean, formally, I don't know. Do you want to know that much? Or
it means that each point of the space has a neighborhood which is homeomorphic to an open set in R2. So this is the formal definition, but we could also just say if we give an informal definition of it, it's just that it looks like an R2, but this is the formal definition.
Okay.
So in fact, two edges with the same label will be pasted together. And furthermore, the polygonal region has to have an even number of edges, because otherwise it won't be possible to apply the proper labeling and CA scheme. A triangle can have the proper labeling applied because it has an odd number of edges, so 3. So they can't be labeled with a label for two edges. And if we pass the edges with the label A together and so with the B, if we do this for the A, B will be an long edge. And that is why the resulted quotient space isn't locally homomorphic to R2. The unit square is a polygonal region with a proper labeling applied. In fact, it has an even number of edges and the labels A and B appearing exactly twice. So when we pass the A together and so with the B, the resulted quotient space is locally homeomorphic to R2.
So elementary operations are useful when one deals with quotient space obtained by passing the edges of polygonal region. So generally, it is difficult to show that a function is a homomorphism. Elementary operations are then a useful tool to solve this problem simply by using simple properties on schemes. So elementary operations operate on the labeling scheme. Two labeling schemes are equivalent if one can be obtained by a sequence of elementary operations. It can be shown that two quotient spaces are homeomorphic if their labeling schemes are equivalent. So here are the elementary operations that don't affect the quotient space. So we have the operation cut, that cut in two pieces a polygonal region. Here, if we set y0 to be the sequence of labels from p0 to p2, and y2 to be the sequence of labels from p2 to p0, we can cut through the vertex p0, p2 here, and label the new sides created with a new label C. And C must not appear elsewhere in the schemes. So we have a reverse operation passed that passed two polygonal regions along the edges labeled C. So here C are the labels from Q0, Q3 and P0, P3. And we can do this operation only if C does not appear elsewhere in the schemes, because we must pass it. And yeah, no.
Sorry, but if the labeling is proper, there can be only two copies of C, right?
Yeah.
So
yeah.
A priori, it should not appear elsewhere. Right?
Well, yeah, but this makes the rules to do the simple properties to.
Yeah, but at this point, do we admit labelings which are not proper? Or
no, yeah, we admit this. So it can be possible that the polygons here are not a proper labeling.
Mm-hmm. Okay.
So we have an operation relabel that replaces every occurrence of a given label by another one that does not appear elsewhere. Permute is just the operation that makes a cyclic permutation. So we cut the labeling schemes anywhere and take the end part to put it at the beginning, a cyclic permutation. And flip is the operation that changes all the exponent and reverse the order of the labels. An intuition to see this operation is that we can see it by flipping the polygonal region over. Cancel is an operation that erases two adjacent occurrences of a given label that have opposite exponents. One more time, this requires that the erased label doesn't appear elsewhere in the scheme. Moreover, here, y0 and y1 must be at least of length 2. Here is for the curious a schematic proof using properties on the previous slides. And we see that y0, a minus 1, y1 becomes y0 and y1. And the last operation is uncancel. And this is the reverse operation of cancel. This operation doesn't affect the quotient space since the reverse schematic proof above can also be done.
Okay, so we'll present a series of non-spaces and how we obtain them from polygonal regions. So first, we will do the labeling of a sphere. So we label a polygonal region's edges and paste the edges with the same label together. So the A together and the B together to give an object which seems to be two cones pasted together. And this object is homeomorphic to the sphere. The labeling scheme is B1, B minus 1, A1, A minus 1. And we have already talked about the labeling of the sphere. So C scheme.
Can you elaborate a little more how you get from the first square with the diagonal to this the two cones? The diagonal is going to be the equator, yes. But can you explain a little more why the top square, how the top square with the two b's coming together becomes this cone?
Okay, so because of the two b are labeled with inverse exponents, so that's why when we paste them together, it gives a form of a cone. It's just like the triangle. So if you look back at the triangle, the labeling of a triangle, you can see that yes, that's one. So you can see that when you have the a when you pass the a together, it makes a cone with an along edge, which is b. And so that this time we don't get the unit disk, but instead of that we just stop to the cone, and we look at I mean we make a space, a non-space, which is a form of two cones pasted together. So it comes from the.
So my question is, let's look at this example at the top. From this triangle with the two A's and the B on the bottom, why do we get a cone? Is it right that if let's say I start to walk along this edge, the left edge, yes, from here, walk a little bit more, and then I go horizontally parallel to B, you walk, and then you end up again at the same point, right? Here, just to emphasize, this is the same point where you started. So when you take this horizontal walk, you come back. And that's why when you identify these two segments, you get this kind of this cone with the base B.
Yeah. That's not homomorphic to the surface. We do not have a description of a cone. Yes, we have. But the logic behind it, it's the same as a cone, and it's the same finally as a unit disk.
Yes, but we just. Yes, but we don't treat the unit disk. We'll just limit ourselves at the cone.
Antoine, Ning, I think it's sometimes more simple than this, the question. You've been trained to visualize very well from the scheme to the surface, and other people who are listening to you are not maybe so used to glue, paste, and visualize the final space.
Yes, understand. So what should I explain now? Or is it all right? Okay. So yes, so the torus can be expressed as the quotient space of the unit square, and we give the edge the label A and B. So the labeling scheme giving a torus from an unit square will be A minus 1, B minus 1, AB. And so it's when we paste the A together, it gives a cylindrical object which is homeomorphic to the torus.
So again, if I take a little walk from the side A and I go up,
yes.
I begin here and I do this little round. So this is the same as a cylinder.
Yes.
And then yeah.
And that was my question from before. Can you just take a piece of paper? This is your paper, and now you identify these two.
Yes. So
when I identify I follow the identification of the square. So I identify those sides to be A and this side to be A, and when I pass the edge, it gives me this sort of cylinder.
Yes, and when you paste the B together in the next step, it gives.
So I have this cylinder, and then I must. I can do it in reality, but you must imagine that this, when you can stretch it and make donut.
Mhm. Very good. Yes, yes, yes.
Okay. So for labeling, okay. This scheme shows the twofold torus and its labeling. And so a polygonal region split along n-1 lines that we name C, with each of the resulted parts giving a torus that becomes an n-fold torus. When we pass the parts together along C, two parts passed it together have to have opposite exponents of the label of C, and it gives n-fold torus. So that one that shows the twofold torus and its labeling, and the next one shows the threefold torus.
So we can see it when we cut this when we cut this polygon in two parts, so the shaded area and the blank area, we can see this as a donut, but without a disk. So we take a torus, and we cut a disk of the torus, of each torus, and we paste it by identifying of the same process, the quotient space, in the two boundary of the disk. So it makes two donuts pasted, and this is a twofold torus.
Yes, so the next one is the threefold torus. And if we understand the labeling of a twofold torus, it is not hard to imagine how we could label a threefold torus. And so we can imagine an n-fold torus. And m-fold plane works with the same principle as, sorry, I should define first the projective plane. So we have to do the same procedures than the torus, but with the labeling scheme AB. So as you can see on the scheme, and furthermore, the projective plane can't be represented in R3. It can only be projected, or should we say immersed, into R3.
So this scary word immersed means that there will be some self-intersections, right?
Yes. That,
yeah.
In a nutshell, it will be just how you could represent it in the R3. So if we give an informal definition of it.
So yeah, in fact, to be immersed in a space, you must have to be there must be an injective map from this space, so from the projective plane in R3. But because there is intersection, this means that there will be this function will not be injective, because there will be two variables that gives the same place, the same point in R3.
Okay, so m-fold plane works with the same principle as a n-fold torus. So we imagine a line C that we split the polygonal region along n-1 line called C, and with each of the resulted parts giving a projective plane, and so it gives an m-fold projective plane. And so, but imagine it is more abstract. So we can, an example of a twofold projective plane is the Klein-Bottle, which is homeomorphic to the twofold projective plane. So the Klein-Bottle is the space obtained from a unit square by means of the labeling scheme. So by the labeling scheme A-1, B, A, and B. So figure indicates how it can be represented as a surface in R3. That doesn't mean that it will be immersed, but it just indicates how we can represent it. So the Klein-Botto is homeomorphic to the twofold projective plane, and not this.
And remark, here we have the same figure as the torus, but in the torus, those labels B were not didn't have opposite exponent, so it was easy to stretch out and paste it in R3. But because they have opposite exponent, we must do some complicated stretch, and this can't be realizable in R3.
Yes, and the Klein-Botto is, it's just like the Mobius band in 3 dimensions. That means that we can make the round without changing the side.
Now all what we've presented can be used to prove our theorem. So the classification theorem. So if we let P be a polygonal region with an even number of sides, we construct the quotient space, P quotient, by passing the edges of P according a given proper labeling schemes. And here comes the classification. This quotient space is either homomorphic to the sphere, or to the n-fold torus, or to the m-fold projective plane, when n and m are equal or bigger to 1. So it can be shown that those spaces are not homomorphic. And for the curious, there is a more stronger version of this theorem that use our classification theorem, and this more stronger theorem state that every connected and compact surface, so we will not define those concepts, but every connected compact surface is homomorphic to one of those same spaces. That's the end.
Okay, so we're done.
Thanks a lot.